In July 2022, I attended a summer school in Cortona, Italy that was focused on homotopy type theory and proof assistance. In short, a proof assistant is a tool that can help mathematicians complete their proofs by giving them new ideas, helps them to clarify their proofs, create things like easily searchable libraries, and can even serve as a certain kind of pedagogical tool. The summer school I was at focused on a program called HoTT, but there's many other proof assistants out there, some of the more famous ones being Lean, Isabelle, and Egda. Homotopy type theory is a new foundation of mathematics, or rather, it's an existing foundation, type theory, souped up with an extra axiom that allows us to identify isomorphic objects. Now, the average mathematician does this callously all the time, but outside the context of homotopy type theory, it may not be entirely rigorous the way in which it's done. So in this video, I'm going to take you through my personal experiences at the summer school. This will happen in the form of miniature lessons about some of the things that I learned about. I'm going to include a number of interviews with people that I met at the summer school. And bear in mind, I went there to learn. I'm not an expert in these topics, and there may be a couple things I don't get perfectly right, especially when we get towards the end of the week and the more complicated things that we discuss there. So I'm very open to discussion about these things in the comment section. Of course, there's timestamps below to help you navigate through different sections. Maybe you're more interested in the interviews, maybe you're more interested in talking about type theory or seeing a proof carried out in a proof assistant. All of this will be included. So let's get to it. My journey began by flying into the city of Milan. There I was met by my friend Elia. We spent the evening checking out Milan. I had one of the greatest pizzas I've ever had in my life, and I spent the night at his place just outside the city of Verona. The next day we made a journey to the city of Venice, spent another night near Verona, and after that we made our way to Florence, where we checked out the Museum of Science, or also known as the Museum of Galileo. Today I'm in the beautiful city of Florence, and behind me is the Museum of Galileo, which contains in it a bunch of historical, mathematical, and scientific artifacts. Things like telescopes and scales and compasses going back hundreds and hundreds of years, including Galileo's actual middle finger. We also made a day trip to the city of Pisa, and of course I had to take the picture and become a cliché tourist. We even came across the statue of my boy Fibonacci. After that, I said goodbye to Elia, and I headed off to the conference in Cortona. It's a beautiful, lovely hillside town in Italy, as you can see from this view of one of the courtyards of the hotel, and the beautiful view from my hotel room. On Monday, as with every morning, we had a splendid stroll from the hotel to the Palazzone, a 16th century building where the summer school took place. Over on the left of this courtyard is where we had the lectures, and to the right is where we had our lunches and working sessions. There was a bunch of cats around as well, but most of them were too skittish to let us pet them. In the first lecture, Gianluca Amato gave us an introduction to type theory. So it's a foundation, sort of like set theory, in which everything that exists is going to be a term of a type. So we can still sort of think about this set theoretically to a certain extent, where you imagine little a, these dots in the big A, means that little a belongs to big A. We say it is a term of type big A. But there's several interpretations that we're going to see in the course of this. Another interpretation that we have of this statement is that big A is a proposition, and that little a is a proof of that proposition. Now, I mentioned that absolutely everything is a term of a type. That means that this thing, big A, that we're considering, that itself, being a type, must also belong to a type. So I'll write U for universe, meaning that it belongs to some sort of universe of types. Of course, one naturally starts thinking about like Russell's paradox, and you think, well, is the universe a term of its own type? And one thing that we do in order to avoid this is that we actually create a multitude of universes, or really a hierarchy of types. There's different ways to index it for certain reasons. We might choose indexing by the rational numbers, actually. That was an interesting idea that was brought up in one lecture. But for now, we're just going to index it by the natural numbers. So, our basic types that we consider all belong to the universe U0. And then in turn, the universe itself is a type. Well, it's something in type theory, so by the rule I dictated earlier, it itself must be a term of some type, which we call U1, and that belongs to a higher type, and so on, etc. We also have some basic constructors, just like in set theory. So given two types, A and B, I can form their product type. I can form what's called the arrow type between them. And again, there's multiple different interpretations of these things. So A cross B can be interpreted, again, like just a Cartesian product of sets, but it's also thinking about A and B as propositions. This also represents the same thing as A and B. You could probably guess then that the arrow type, A to B, consists of all those types, which we think of as somehow functions between A and B. And one thing that's really cute is that now our notation, if I write F as a term of the arrow type A to B, this aligns with our usual function notation. But this also corresponds to the logical implication if we're interpreting A and B as propositions. One really interesting and important feature is also the dependent product type. So the dependent product type is a sort of product where the factors of the product can change. They're sort of indexed by this basic type A below. As a particular example, consider the case when it's just constant. What does this refer to? So this is just B in every single term here. So what would a term of this whole type look like? Well, it simply says that for each x in A, you're selecting some term of B. So this can actually be identified with the arrow type from A to B. So now it's like that we're having a function from A to B, but the codomains change for every input in A. And the logical interpretation of this object here is saying that for all x in A, the proposition Bx holds. In fact, as you can see here, there's a whole table of different symbols, different basic constructors we have in type theory, and the different interpretations. This picture is from the HoTT book itself, and you can see there's already a hint of something we're going to talk about in a few moments, the homotopy interpretation of all of these symbols. In the afternoon, we had a lesson about some of the basics of programming in Coq, and our problem sessions involved us actually starting to code some of our own proofs. So I'm going to give an example of a proof here that I think is pretty instructive. So I have Coq open here in VS Code, and we can see I have this definition / theorem because when we're working in type theory and proof assistance, I mean, in some sense, you need to prove that a definition is valid, right? So, for example, if I'm thinking about A, B, and C belonging to U here, my sort of base universe, if I'm thinking about these as sets, I am, in some sense, by defining the set, I'm proving to you that the set exists. Alternatively, we can think about this as a theorem in which I'm proving that this proposition follows here. So let's go ahead and see how we actually go about proving this. So I'm going to hold Alt down, and now we see on the right side of the screen, I have something that keeps track of my goals and my hypotheses. So we can see that on the right-hand side, I have my hypotheses that A, B, and C are of the universe UU, and that I have, well, it's just my initial hypothesis. Not much is different from the original statement. So how do we crack this open? Well, ultimately, I have these, we can think of the x's as and symbols or products. I have this whole, concatenated ands, and that is implying C. So I have some sort of implication, which means I need to start with the hypothesis and reach the conclusion. So what I'm going to do then is I'm going to type intro H and put a dot at the end. And now that I've put intro H, we can see what was my hypothesis in that statement has now been promoted up to my hypotheses on the right. And the goal of proving C ultimately is now just my one remaining goal, right? So before, my goal was proving the whole thing, but then I assumed the hypothesis, and now my goal is simply to establish that C is true. So how can I do this with the materials that I have available to me, with the hypotheses available to me? Well, if I look at H, I notice that I have some term involving a C there, right? It's the sort of first coordinate. So again, we're going to go back and forth between thinking about this as sets or propositions. I have my first coordinate in this product is A cross B arrow C. So what I can do is set, now I need to come up with some names. So I guess this is my next hypothesis. I'll call it H1. And I'm going to let it be the projection on the first factor of my hypothesis H. So now applying that, we can see I've now gained the hypothesis H1, right? Because I know if I'm assuming H, I'm assuming each of the individual factors to be true. So now I can use this to augment my goal a little bit. So what I can do is apply this, right? Because right now my goal is to prove C, but by using H1 tells me that instead of proving C, it's enough to prove A cross B, because that implies C. I have that in my hypotheses. Great. So I apply H1 and I hit Alt down, and sure enough, that's what happens. My goal has now changed from proving C to proving A cross B. Fantastic. Now, at this point, we realize, well, how do I prove A cross B? So again, thinking in proposition mode, this means that I need to prove that both A and B are true. So what I can do is apply a technique here called T-pair. And now watch what happens as I do this. It actually splits up my goals. So now I have two goals. Goal 1 out of 2 is to prove A. Goal 2 out of 2 is to prove B. And the tactics that I apply will happen in order that the goals appear on the right. So I see that I want to prove A, right? Well, how can I do this? I look back up at my hypotheses, and in our original hypothesis H here, we see that there is A. So we might think that I'll just go, oh, set, and okay, I'll call this hypothesis 2, and I'll call this the third projection of H, right? Because there's 3 factors there. Wait a second. The reference projection 3 was not found in the current environment. So now we almost got to put on our categorical thinking hats. How is a product defined in terms of a universal property, that is? We have projection 1 and projection 2. So there's really only 2 projection maps. There isn't a third projection map. We sort of have to think, before we've proved that, say, set theoretically that A cross B in brackets cross C is in bijection with A cross B cross C. We can't simply use this assumption. So I have to go back now and I'll try projection 2. There we go. Oh, but wait a second. What is this in H2? That doesn't really look much like at all what I thought it was going to be. Well, sometimes the expressions get a little bit complicated as they're parsed out, but thankfully we have this wonderful little tool, CBN, for combine. So I can write combine in H2, and that simplified the expression. Now it looks like something I can use. Well, I don't quite have the assumption I want, though, right? I'm trying to prove A, and I see it. I've got the assumption of A in there. So I'm going to need to use my projection once again. Now, by the way, I'm sure there's some people watching who might know a little bit of calc, and I'm certainly not making the most efficient proof that I could, but I think this is somewhat instructive, to get the very basic low level of this down. So I'm going to take the second projection of H2 now, and I hit Alt down. I hit Alt down. I hit Alt down. No true coding tutorial of any sort is complete without some mistakes. And now, finally, again, we see we have this messy thing, but we just learned about how we have this nice little tool that helps me clean up my expressions. And great, now I can simply, if I'm trying to prove A and I have the assumption A, I can simply apply it. And now that goal has been proved, and thus it disappears. Notice, too, that if I go back one step, the other assumptions disappear as well, the other hypotheses. This is because I've essentially split this into two separate cases, right? And so in one case, I may be doing reasoning that is only available to me in one of those cases. So our previous hypotheses have disappeared. Now, how are we going to prove B? Well, we go back to looking at some of these assumptions that we have. And I see again that I have A, and I have the assumption A implies B. Great. So we can already see that there's a bit of redundancy happening here, right? So again, I'm not taking the most efficient path, but somewhat on purpose. So naively, we might say, okay, set H4 to be, well, let's see, maybe H2 is already saved in our bank somewhere. So I'm going to let that be the first projection of our assumption H2. And what happens when I do that? It didn't like it. So I go back and I will let this be projection 2 of H yet again. And again, I find that it's kind of messy, so I'll go combine in H4. And I want both of those projections, so I will set H5 to be the first projection of H4. And before I even type the next down arrow, I can already see that I'm going to want H6 to be the second projection of H4. So I'm going to go ahead and set both of those up. Great. Now I have all of the assumptions that I want. Again, H6 looks kind of messy, so I might combine in H6. And of course, typos are great. Fantastic. So now what I can do is I can see that I could apply H5 to take my goal of proving B and use the fact that it's sufficient to simply prove A. And then finally, I can apply H6, and that finishes the proof. And in fact, one thing you can type here at the end to wrap up is QED. That afternoon, like most, we walked into town to have an aperitif. Then after having an amazing dinner comprised of local food and wine, a number of us hung out in the hotel bar to discuss mathematics, philosophy, linguistics, play chess and piano, and just generally enjoy our time there. On the Tuesday morning, we got an introduction to the homotopy part of homotopy type theory. So that is those types that we were talking about before that we realized we could think of as being like sets or propositions. We started to think about those as spaces. So now our types, like big A, some type, we now think of as some sort of topological space up to homotopy. And we conceive of the terms of that type as being points in that space. Okay, so far it's not extremely different, at least for terms belonging to a type, than the set theory interpretation. But things start to get a little bit more, here's where things start to diverge a bit, is that suppose I have two terms of the type A, then an equality between two terms of that type we actually think of as being a path between those 2 points. So now there's a geometric interpretation to the equality. And here's where things start to get really interesting, because just like in homotopy theory, you can have paths between paths, right? You can have a homotopy between paths. So now, and so I should say, even before the homotopy interpretation, this statement A equals B, little a equals B, this is a proposition, and therefore it is itself a type, and therefore it can have inhabitants if it's true, or it is uninhabited if it's false. So we can have two, suppose I have 2 inhabitants of this type. Well, now in the homotopy interpretation, I can also conceive of these as paths, and those themselves could have a homotopy between them. So within the equality type, P and Q could be equal as paths. And now we can keep going, right? This in turn could have some terms, and those terms might be equal, and so we can have paths between paths between paths between paths. And so ultimately the conclusion is, now that we're conceiving of these types ultimately as infinity groupoids. So if you're not familiar with this concept, the intuitive thing you can think of is just how in a topological space, you have paths between points, you have homotopies between paths, and you have homotopies between homotopies ad infinitum. So now, since we have a notion of homotopy, that means we also have a notion of contractibility. So, one can define this operation or this type, I should say, is contractible, right? So is contractible is going to be the sigma type. So we're going to go over all x in A. So remember, there's also an interpretation of the sigma type as being the there exists symbol. So there exists an x in A such that for all y in A, there is a path from y to x, or in other words, y is equal to x. So this is our definition of what makes a space contractible, although one has to meditate on it for quite some time to see why this is the right definition of contractibility in this context. But okay, I've given you the formality. Again, you can just think of the intuitive thing being that you actually think of that space as being geometric in some sense, and that it's contractible in the sort of classic homotopy interpretation. So then there's also a notion of equivalence, and I'm not going to write down the full technical thing, but in short, if I have some sort of arrow from A to B, then I'm going to say it's an equivalence if the fibers are contractible. So again, writing this out becomes a little bit technical to do it properly with types, but that's essentially the intuitive notion, which if we're thinking geometrically, if we're thinking in terms of sufficiently nice topological spaces, this essentially is what a homotopy equivalence is. But now we're using this idea to define an equivalence of types. And so I can form now, in the same way that I can form, say, the type of equalities, I can also form the type of equivalences between A and B. So this one I will define for you just to see it. So it's basically all of those arrows from A to B, which are equivalences. So sometimes we write this as a type is equiv, right? So the type is equiv would be inhabited if F were an equivalence. And so we're somehow bundling all of these up together. And that was actually a little bit of foreshadowing about the other interpretation of the sigma type, which I will get to in a moment because it leads to a really interesting proof that 0 is not equal to 1, which I'll do for you properly in the Coq proof assistant. But let's explore a few more things alongside this idea. In particular, we know that an equality gives us an equivalence, right? If I have two topological spaces that are literally equal in terms of their underlying sets and topologies, well, then clearly there's a homeomorphism between them. It's just the identity map, right? So we have a way of taking, in general, this sort of idea can be formulated in terms of types. So one way to say this is to prove that there is an arrow type between the type of equalities between two types and the type of equivalences. So now, though, we get to the real sort of the univalent part. This summer school I went to was called Summer School on Univalence. And what this is, it's an axiom that essentially says, so the univalent axiom says this, that this is an equivalence itself. So in other words, the type of equalities is equivalent to the type of equivalences. And what this means now is there really is no distinction between equality and isomorphism, if you will. And I mean, this is the way that mathematicians typically behave. So in some sense, as this foundation is being built, it's sort of being reverse engineered in a sense to already conform with the way that mathematicians are doing mathematics. We somewhat abusively treat isomorphic objects as the same, even though they're ultimately not. We need to prove that certain constructions, like the fundamental group, is actually a homeomorphism invariant. But now in type theory, isomorphism being the defining feature of equality essentially is now baked into the foundations of the theory. So going on a bit further, now in the basic notion, I did say that we can think of all types as being propositions in a certain sense. However, there's some that behave more classically like propositions than typical, let's say. There's types that really behave as propositions in the way that we typically conceive of them in set theoretic based logic. So we're actually going to say that a type A is a proposition precisely if all the equality types themselves are contractible, right? So the sort of most boring atomic element that could exist is just a contractible space, right? It's essentially just equivalent to a single point. There's not much interesting there. So what's the, topologically speaking, what's the next level of interest? That is a space in which the equality types are all contractible, right? So there's paths, but the homotopies between those paths are all trivial. So not contractible, but all the spaces of homotopies are contractible. We're going to say that A is a set. So again, I talked before about how you can sort of think about terms belonging to a type sort of like sets, but it's not an exact one-to-one correspondence. And in the world of univalence, where we've now introduced this univalent axiom, right, you have to think, well, for the set theory world, equality and isomorphism are very different, right? Because an isomorphism between sets is a bijection, whereas equality is this literal equality of elements. They have to be comprised of all exactly the same elements. So this univalent axiom would sort of seem to break set theory if we were trying to interpret all types as sets. However, just like with propositions, there are some types that really behave like sets in the classical way that we think of. And so it turns out that A is, we're going to call it a set because it will behave like a set if the equality type for all x and y in A is a proposition. Or another way to think about this is that if so the x and y do not have to be contractible, but for all x and y and p and q in that x and y, the equality space of those paths are contractible. So essentially what you can see is that we're moving towards is that this is basically corresponds to homotopy levels, right? So we would call this homotopy level 1, homotopy level or 0, 1, 2, and so on and so forth. And if I'm remembering correctly, the third homotopy or the next homotopy level is where you start to see structures like groups or monoids or vector spaces. And the next higher homotopy level is where you start to see categorical structure. I'd like now to jump back and revisit this idea of the sigma type and the pi type. What exactly do these things mean in the homotopy context? Well, as my hint sort of suggested, they can be thought of as related to fiber bundles, or actually more generally, because we're thinking homotopically, fibrations. So ultimately, we conceive of the sigma type as being a fibration, where in this case, we think of the base space as being A. And, as we vary our points X, we get these, these different fibers above it, B of X, in this larger, this sort of larger space, which would be our actual fibration. And then the way that we conceive of the pi types is that these are sections of that fibration. So what I mean by that is an element of this object is a section of the, the projection map for the fibration. Because again, if we think about this, when we were conceiving about this pi type before, we realized that we could really think about f as being a function which the codomain changes with the input values. But maybe a way to articulate that a bit more clearly is to actually have some sort of space that gathers up all of the B depending on X, which the sigma type does as a fibration. And then we can really think about F as being a map from A into this fibration sigma, but in such a way that it is a section. At a point X, it picks out a specific point in the fiber above X. This is a really important idea when it comes to the notion of transport. So let's pause on the homotopy theory for a second, and let's just go back to thinking about, when I have this sort of this sigma type or this pi type, B of X. And now suppose that I had, so these are both happening over A, let's say. And suppose I had two elements, X and Y, and, or rather I should say two terms of the type A, and suppose that these are equal, right? So these both belong to A and they're equal. The homotopy interpretation being that there's a path between them. Now, I would like to say that somehow B of X should be equal to B of Y. But ultimately, there isn't really a way a priori to relate these two things, Bx and By. It's not exactly clear that they should even be related. But in the homotopy picture, we conceive of this as, again, we have our base space A down below here. And now if we have two terms of A, being X and Y, to say that they're equal simply means that there's a path between them. And this brings us to a very important concept now. If we could think about our fibration above A, we get a very important notion known as transport. And so this idea of transport, essentially what it does is it takes a path between, so I'll call this P, path between X and Y, and it lifts it to a path from Bx to By. So now it says if you have a path from X to Y, then you have a path between Bx and By. So now we're just about ready to actually carry out the proof that 0 is not equal to 1 in univalent foundations. And in fact, we'll do it in the proof assistant. So spoiler alert, this is what the proof looks like. But if you're unfamiliar with this, it's probably not clear why exactly this is a proof. So there are a couple pieces of terminology I'm going to need to explain first before we actually go through line by line of the code. Now, one thing to recall, if we think about sort of classical logic, proving a statement is false is equivalent to proving that that statement implies false, right? So that is actually, this is what we're going to take to be the definition of falsehood in type theory. And remember that for us, a statement being true or not corresponds to it being inhabited, and its inhabitants are proofs of that statement. So for us, false is just the empty type. I'm going to use the empty set symbol here. So in other words, we're trying to prove that some statement implies the empty set, right? So in other words, proving that 0 is not equal to 1, right? Proving 0 equals 1 is false. This is the same thing as proving that 0 equals 1 implies false, right? The empty type. And technically, right, I've already abused the notation a little bit. I should say where this equality is happening, right? This is an equality in the type of natural numbers. Now, how are we going to go about proving this? We're actually going to put on our topology hats in order to prove this. So remember that the type of equality, 0 equals 1, is really a type in itself, right? And so the implication arrow has this other interpretation of essentially being a function. So we can think of this as like we're defining a function from the type of equalities 0 equals 1 in the natural numbers to the empty type. So how can we possibly do that? Well, there's a good reason I spent so much time talking about transport. Remember that elements of an equality type we think of as being paths in the larger space, right? So now I can draw this picture where I have the natural numbers, right? And I've got, here's 0, here's 1, and they keep going. And imagining that I have something in the equality 0 equals 1 is like imagining that I have a path in this natural number space. So how can I get from a path 0 equals 1 into the empty set? Well, if I had some sort of space above this, right? If I had some sort of fibration, and the fiber above 1 was the empty type, and I had something in the fiber above 0, I could then use this idea of transport, right? It's essentially this homotopy lifting property to then get a path up here, right? So what's one thing I might put the fiber above 0? Well, I could put the type with one term. And this is something that, well, technically I haven't proved it for you, but this is something is maybe more believable. We know that these types aren't equivalent, right? So therefore, we would obtain essentially the contradiction that we're looking for. And remember, we generally drop the law of excluded middle when doing this kind of mathematics. The proofs by contradiction, where you prove that something exists by proof by contradiction, are out. But we can still prove that things don't exist by contradiction constructively. So to carry out this proof, then, I need to construct this fiber bundle, if you will. And while I haven't gone into extreme detail about this, we're actually going to use the sigma type construction, where it looks a little bit different because normally we think about defining, say, like a fiber bundle in terms of a projection map. But what we're going to do here is essentially like the way that the sigma type works is we sort of tell it what the fibers are above each point, and then it says that we can essentially form this bundle. So What I mean by that is I'm going to create this definition, right? I'm going to call it bundle, okay? And how am I going to define it? Well, I'm going to write for each natural number, because I'm thinking about this as my base space. I want to tell it what the fiber is above that point. And where's that going to take values? Well, I'm actually going to take it, have it take values in the universe of types itself. Because remember, I want the fiber above 0 to be the unit type, right? This type of one term, and the fiber above 1 to be the empty type. So, well, where do those types live? Well, it lives in the entire first level universe of type. So why not create this bundle where that is, you know, the total space, part of the total space. Okay, and something else I haven't gone into extreme detail about is recursors. So every type comes with a recursor. This is essentially how you construct things for that type, right? Remember, we're doing everything computationally here. So the natural number recursor, as maybe, hopefully makes some intuitive sense, is really just induction. Right? Like that's normally in a constructive manner. How do we build something for every natural number? We use induction, right? So what I need to do for the natural recursor then is I need to tell it exactly where I'm going to, well, how does induction work? I need to tell it where it sends 0 and where it's, if I know where it sends n, where does it send n plus 1? And again, 0, we know that we want to send that to the unit type, right? So I'm just going to say, okay, send 0 to the unit type. The recursor knows, being induction, that what I'm writing first is where I want it to send 0. Remember, we want 1 to get sent to the empty type. And no part of the sort of sketch that I just drew did we actually care about what the rest of the natural numbers are doing. So we could just make our life easy on ourselves, and we could send all the other natural numbers to the empty type, because it doesn't matter, right? What's really important is that the fiber above 0 is the unit, and the fiber above 1 is the empty type. And let's just make sure that our definition works. Great, the code compiles. This is a valid definition. We've now constructed this object. All right, so now we're ready to prove this theorem. So what is the theorem? 0, 0, not 1. So we can see that name is already saved in my bank because I've proved this before and I'm used the same title. So theorem 0, not 1. Okay, what is this theorem that we're trying to show? Well, I want to prove that 0 being equal to, so much like in any other foundation of mathematics, you know, we start, when we construct the natural numbers, you know, the successor of 0 is 1 and so on and so forth. So I'm going to write 0 equals the successor of 0. If that's inhabited, well, then that implies a falsehood. The statement compiles, and now it's time to do the proof. As always, I'm going to begin with intros H, let's call it, right? So let's go intros H. And so again, now we can see, right, on the right-hand side, I have my the statement, which is to be proved. 0 equals the successor of 0 implies the empty type, right? Implies a falsehood. So intros takes my assumption, right? So we now see up top, I have the assumption 0 is equal to 1, and below is the goal, right? I'm trying to prove a falsehood. And remember, we just defined this bundle in order to use it, right? So somehow I need to bring this bundle into this proof, right? This proof needs to know about this. I need to bring it into my assumptions. So I'm going to pose, what am I going to pose? Well, it's not just this bundle specifically that I want, but I want to use the concept of transport, right? So I have this bundle, it's already constructed, and I have a path from 0 to 1 in my space, and I want to use transport to get the lift of this path in the bundle. So what I do is I say, okay, I'm going to use transport on this bundle I've just constructed, but it needs to take in a path, right? I'm lifting a specific path. What is that path? Well, it's h, right? If we look in our assumptions, we assumed 0 equals 1, which is to say we assumed that 0 equals 1 is inhabited, and we called a specific inhabitant of that equality type h. So I'm going to apply this to h. And so now we see that we've used pose, and now we have up above in our assumption, we now have this b. Cock has come up with a term for this this b for us. This is a path. This is the path that we're looking for. Now, of course, as written, it looks a little complicated, right? And our secret tool, like before, is we use this combine function, right? So I simply use combine in b. Okay, now it simplifies it a little bit, and it tells me, okay, b is a path from the unit to the empty type. And, right, so it's unit implies empty type. And look, I have in my goals the empty type. So just as before, I can apply b to change my goal, right? If I can prove unit, then by b, it implies the empty type. So if I apply b to my goal, that now moves the goal. Cock understands I just need to prove unit. But unit is true, right? This is identified with the truth value true, right? This is inhabited. It's the type with one inhabitant. And the inhabitant that we normally call it is just TT. Oop, I made a little typo. And so this should compile, and there we go. We have proved that 0 is not equal to 1. Tuesday evening, we had a talk by Dr. Kevin Buzzard. We also had talks from people like Daniel Grayson and Terry Cockand himself. I don't have any notes from those talks, and it's been a while, but you can catch an interview I did more recently with Kevin Buzzard on my channel. Wednesday was a free day, so a lot of us spent the morning, well, just sort of working on exercises, both in Homotopy type theory and specifically programming them up in Cock, which leads us to probably my favorite picture of the whole conference. So here we are, working in a room. On my computer is the cutting edge of math, essentially, right? We're doing like category theory in a proof assistant and the formalism of univalence, and in the background is a 16th century fresco. I just love the meeting of worlds in this picture. Most of us then decided to take the afternoon off, explore a bit of the countryside of Cortona, and I even went to a lake with a few friends. We had a dip, had some drinks, some gelato, and that leads us to our first set of interviews. So right now we're at the beautiful Lago Trasimeno. We have an evening, or the afternoon off after a problem session today. So we figured we'd come here, go swimming, have some gelato, have some beers. I'm here with my friend Simon at the moment. Florian's also joined us at the beach today, and in fact he studies at the University of Calgary with me. We both started back in the fall, and we had a little bit of a reading group to prepare ourselves for this summer school. Do you want to tell us a little bit about what you currently do in terms of research?
Right, I'm an algebraic topologist at heart. I'm a homotopy theorist, so I look at gauge groups of principal bundles from the homotopy type point of view.
Mainly I'm trying to understand tangent infinity categories and what structure is in there. And for this I both have to understand tangent categories and infinity categories. And that actually connects with the school here. Like, I'm getting practice with infinity categories.
So it's maybe safe to say you're here more for the homotopy inspired reason.
You could say I'm a tourist.
Right,
I'm a tourist
right.
of homotopy type theory.
Right.
That's one reason. The other reason is that I always wanted to learn more about logic, and I always liked programming. So the ideal combination seemed to me programming logic.
In your experience of the school so far, what's something that you learned that you're particularly interested by?
The idea of proof assistance seems very appealing to me. But so far, what we've seen is very low level. It's not powerful enough to sort of deal with the kind of stuff that I'd like to do.
proving that 0 doesn't equal 1 using vibrations.
It's cool. And it's correct.
Yes.
But it's not necessarily the kind of stuff that would excite me. But,
Right.
I really like seeing proofs as elements of things and seeing implications as functions. I find this gives a great new perspective.
Could you perhaps distill one thing you think you'll take with you from this summer school?
Yeah, definitely the idea of sort of thinking of proofs in sort of algorithmic terms. Right.
Awesome. Thanks.
Oh, you're welcome.
In my everyday work, probably very little, but I've definitely seen that using proof assistance is just great fun.
Fantastic. Thanks.
Here with my friend Tom, and chatting with Arnaud. Why don't you tell everyone a bit about where your current research is?
Oh, so I don't really have current research. I work in the tech industry. I live in Cambridge, in the UK. I was formerly a mathematician. I finished my PhD in 2017.
Is that then what brought you here? Was it that you saw this as sort of a way to help keep that connection with the mathematics world?
Yeah, in effect. And so I'd always, as a PhD student, I'd seen a few introductions to homotopy type theory, and had never quite clicked with it. And then it had always been on my to-do list to really kind of look into it in more detail.
Well, I'm almost a qualified algebraic geometer, I believe. I've almost finished my master's thesis in algebraic geometry, number theory, that kind of stuff. And I have been studying computer science for some time now. Benedict Ahrens, one of the organizers of this conference, he will supervise my thesis. And he invited me here to learn a bit more about the whole context this thesis will take place in and the things we'll be studying.
So far out of the things we've learned about and worked on in this summer school, what's maybe one highlight, a concept that you learned about or perhaps was reinforced or reinterpreted?
So I think probably, the whole kind of, the way that the Unimath library works. I played around with Coq and some of the other homotopy type theory repos and proved some things, but I didn't know how the Unimath library worked and what the conventions for that were, with the view to potentially even contributing to it in the future.
Well, I've seen much of the material before, but I've seen them now in a slightly different order or slightly different groupings of material, and I think that's very helpful. Like pouring cheese over hot macaroni and seeing it melt, and then just jumbling the macaroni around and having all these threads that kind of binds it all together. And also there were these kind of specific things like I've seen functional extensionality, proof irrelevance, univalence. I've seen them before, but now there was this one lecture in which they were just presented on one slide, and their relation was explained, and that was very insightful for me.
What are one of those things that you see yourself really sort of using in the immediate or perhaps somewhat distant future? Is there one of these principles that you really see yourself incorporating into as you continue to learn about this and develop it?
Absolutely, I've made some contacts here, and I've got ideas for research in terms of what we can do with. So my PhD was in an area called rational homotopy theory, and I think a lot of that can be formalized in Coq and should be formalized in Coq.
Thanks.
There it is.
I believe I'm currently at the building general knowledge stage. So any knowledge is welcome. And I mean, I'm gaining a lot of experience with working with Coq here, which is very useful. So because I will probably be using that in my master's thesis, maybe in some hobby projects. So
that's great.
So definitely, yeah.
Yeah, awesome. Well, thanks.
The final 2 days were also filled with more adventures in the area, getting drinks and dinner in town. We had a bunch of other great lectures as well, including homotopy type theory focused on the set level, and doing actual homotopy theory. We proved that the fundamental group of the circle is the integers in homotopy type theory. However, I'm going to leave a lot of the rest of this material for you to explore yourself, either in the homotopy type theory book Or, recently, Egbert Reika has published his own book. There's a freely available version of this available on the archive. Before I went off to explore the south part of Italy on my own after the conference, I managed to get in a couple more interviews.
So we're standing out in front of the beautiful palette zone with Margot Majuzzi.
So I'm here with Benedict Arns, one of the organizers and presenters of this event. Can you maybe start off just by telling everyone a little bit about the research that you typically do from day to day?
Hi. So in my research I'm interested in two things. On the one hand I'm interested in the theory of type theory, means the theory of the syntax and the semantics of type theory. And on the other hand I'm interested in practical formalization of mathematics and results in mathematics and computer science within type theory.
Oh yes. I come from algebraic geometry several years ago now, and I get involved in one of those projects about formalized mathematics, and slowly I moved more on topics in computer science, but I didn't quit geometry completely actually. I still had things that interested me in, for instance, in quaternionic analysis or complex geometry. So I try to keep a good balance between more classical topics in mathematics and some new computer-oriented topics.
Well, and hopefully one day they'll completely converge. Yes, yes.
And so what were some of your personal motivations in wanting to put this summer school together for all of us?
Well, it started out with an idea that we had with Vladimir Vovotsky. He said he had some money left because he was supposed to organize a conference, but he didn't actually get around to doing that, so there was some money left. And he asked me, do you have an idea what we could do with that money? And I said, well, let's organize a school. Let's teach young kids, let's teach young people how to use a computer-proof assistant, how to formalize mathematics and univalent foundations, and grow the field. Because for Vovotsky, it was very important to bring computer-proof assistance to the masses.
Yes. So there is this project of formalizing mathematics in general, and in particular using the univalent foundation started by Voevodsky more than 10 years ago now, and we would like to attract new people, and so the school is a way to teach to the people this new foundation of mathematics, and at the same time a way to find more people interested to actually contribute in the field.
And for those people who are interested watching at home, what are some ways that they can get involved in the proof assistant community, or some good starting tips?
I think if you're motivated to learn, there's a lot of material out there. In particular in the recent years with the pandemic, people recorded a lot of videos, people put a lot of videos and material online, and then asking for help. I think it's very important to ask for help and to not be shy, and this can very well be done on these new channels like Zulib or mailing lists, but Zulib in particular, I find the community is very, very active on Zulib, and I would encourage everyone to go there and ask plenty of questions, whether they are like smart questions or very naive questions. It's very important to not be scared to ask questions.
Yeah, I think that's pretty good general advice for learning most things, is letting go of that fear of asking questions and making mistakes.
So of course, doing schools like this one and many others that are organized can be a good starting point. But also, my impression is that they are very open scientific communities that accept contributions and way to share the knowledge in many different ways, with websites, books of course, as in any topics, and also many channels like chats, forums. New people are very welcome in general.
Okay, thank you very much. Thank you very much.
Thank you.
So I'm with my friend Walid Marzuga, just here on the very last day of the conference. Here chatting with Felipe Nucho, Adriano Barile, and well, so what do you normally do in your research typically?
Well, I'm a PhD student in the computer science department in Turin, Italy. So my PhD research goal is it's actually, a green goal, but I don't know how much, green I can get, but I really hope so. And it's in reversible computation, so it's, computation paradigms that go, both directions.
Well, I'm technically not doing research right now. I'm just taking courses. I'm about to start my second year PhD, but I'm poking around, trying to find different kind of areas I'm interested in, and I've always been interested in logic, and homotopy type theory is obviously tightly related to. So I was thinking it was a good idea to participate in this summer school.
Well, I've been formalizing mathematics now for a couple of years in a different theorem prover rather than Cork. I was mainly using Lean. And I'm a classical mathematician, so I've never been interested, well, at least not for scientific reasons in homotopy type theory or in set theory. But well, I'm enjoying formalizing math, and so I thought I would give it a try to some different processes and different foundations to understand how it works.
So then I guess you sort of came to this school inspired a little bit more from the computer science aspect of
Well, not quite actually, because I have a mathematics background, and it was kind of a schizophrenic path where I was into geometry and also into algebra and also into logic, like differential geometry, mathematical physics, and then I got more into logic, and then I had a bridge towards the computer science department that did all the prohibited stuff like type theory and intuitionistic like constructive mathematics.
What's one of maybe your favorite lessons or lectures that we've had so far in the summer school?
Well, I enjoy all the lessons for sure. I had a slight preference in theoretical lectures. Maybe my favorite one would be, if I had to pick one, it would probably be surprisingly the Blavatsky lesson.
The historical perspective,
because it actually gives you a little bit of context of what's going on. Jumping in straight into the homotopy type theory. That's how you're not telling students that's how things have to be done. You have the historical part and the motivation. I think that's really important.
Today's talk by Benedict on set theory in Cork and set theory in homotopy theory, what it means for a type to be a set, is a completely different viewpoint from the one we use in Lean. It's also different from what we use in classical mathematics. If you're not used to it, I realize that it can be mind-blowing a little bit. I've been trying to define what a quotient is for the whole 1.5 hours of exercise training session, and I went nowhere, absolutely nowhere. So now I'm back to trying to discover what a quotient is, but okay, that's fine. But it was very similar to the talk, I think.
So I know you'll take a lot, but is there maybe one particular lesson you can say that you can point towards that you might take, some particular lesson or tool or concept that you see yourself using in the near future?
Well, one thing is of course using theorem provers like proof checkers, even if it's not univalent, because that's the thing I have to think about. It's not like, oh, now I'll go home and have a flag of univalent mathematics with a univalent action, and I'm like, yeah, this is the thing you should show. But even if it's not that, it's some kind of constructive mathematics that you're building together as a community.
So I think like one of the most important thing is like mathematics and programs are actually hand in hand. At least if you want to work in logic, in my case. So I'm going back to computers.
Concerning the Uni-Valley foundations, I'm still wondering if this has, if it has a true added value to the way a mathematician think about. I hear about mathematician, I read define a mathematician by subtraction. Mathematician is someone who typically knows nothing about foundations, knows nothing about the logic they've been using, and so really not by saying that we know more about, but typically we know much less. And I don't know if I haven't fully understood yet if this theory, this culture would add something to a mathematician's reasoning, or if it's just very interesting, but at the end of the day, maybe a bit too abstract. This I don't know yet, honestly. So I'm uncapable to say.
When people like asked me when I was like 19 or 20, so you do mathematics? Oh, you're really good at counting. And I was like, no, like machines do that. And now I'm like, oh, you're a mathematician or / computer scientist. You're really good at proofs. And I'm like,
no, the machines do that.
Yeah, the machines do that.
Well, thank you very much.
You're welcome. Thank you.
Thanks.
Okay, thank you.
Well, thank you so much.
It was a pleasure.
So I'm with my friend Walid Marzuga, just here on the very last day of the conference. We're walking towards the pellet zone, and I'm just wondering what is one of the things that brought you here to this conference in particular?
Italian pizza.
And out of all the lessons we've learned so far, what do you think is the most impactful out of everything we've learned?
I'd say, without any doubt, Italian pizza.
Of course, naturally. And what's one of the things that you think you'll take home with you and incorporate into your own work in the future?
Italian cuisine.
For making me a mathematician because of your shit posting.